morning, everyone, and thank you for joining me today here. It's a pleasure for me to be here today. Today I'm going to talk about how traditional optimization techniques can be combined with location intelligence in order to build a powerful optimization algorithm that can be applied, for example, to improve traffic in large cities. So these two pictures, I took them in the last 2 weeks on 2 random days, and this is on my way to work. So every day when I go to work, I use my bike to go to work and go back home, and this is what I find every day. As Paula said, I live in Madrid, which is a city with a very poor bike infrastructure, so that means that I have to share the infrastructure with cars, and this makes it quite difficult, sometimes even very inconvenient, because if there's traffic for me too, even though, I consider that I'm doing something good in order to reduce this traffic. And a while time ago, I started taking a closer look at the cars around me when I go to work and when I go back home, and I realized that more than half of those cars are taxis or rideshare vehicles, and among all of them, more than half of them are empty. So if you go in the morning, like this is Gran Via Street in Madrid, if you go there and you take a look at the taxis and rideshare vehicles, you'll realize that most of them are empty. So taxis are looking for some clients to flag them and stop them, and rideshare vehicles are driving so that they trying to find a high demand zone so that they get assigned to a trip service, let's say. When I realized about this, if you think about it, traffic is one of the main sources of pollution in large cities, and car infrastructure takes a lot of the space that in cities that we could use for bike infrastructure, for example, but also for parks or simply larger wide sidewalks for people to enjoy their cities. So the idea today here is that I'm going to introduce you to optimization, how to apply optimization in order to let's think about an alternative and how we can think about this service and provide it in a different way. Before I start, we all know that the service that taxis and these rideshare companies provide in cities is essential, because not everyone can take a bike or public transportation. If we think about elderly people, they probably cannot go and take a metro or a bus because they just can't. So this service is essential. So here, what I thought about is, what if we could think of new legislation, because we've seen with rideshare vehicle companies that some time ago they said, okay, we are here to reduce traffic, but the truth is, for example, at least in Madrid, that traffic is even worse. So I think a new legislation is needed here. What if we had a new legislation in which, for example, we couldn't flag taxis on the street, so they had to wait in certain locations throughout the city, or you could order some taxi service through an app, like you do for others, but just for everyone, so for taxis and also rideshare companies. So based on that, the thing is, since this is a very essential service that cities need, we need to have a fast response. So when I need a taxi, so today I'm used to having a taxi when I need it. So I just go down the street and I flag a taxi, I get a taxi. It's very fast. So how can we make this fast, but without having taxis and without being able to flag them while we're on the street? Okay, so this is my focus today is going to be on how we can apply optimization in order to reduce these times, these waiting times, let's say, while at the same time reducing the amount of traffic that we have in the cities. So this is the problem that I want to solve, and if we think about this problem, these are the components. If we think about the components from a mathematical point of view that we have to solve this problem, so we have the driver's current position, so they are located in certain places. They can be like driver A, they can be serving an order, so they can be traveling so taking one person from one place to another, or they can be idle, like driver B, at a different location. And then we have the pickup points and the drop-off points. So the places where we have to pick up customers and the places where we have to drop them. Okay, so if we think about this, we have different locations. We have to drive from one place to another, and as our goal here is to minimize the empty driving hours or empty driving distance in this case. So what I have are different nodes in my city, and I have different connections from one place to another, and I have the distances from one place to another. So basically, I have a network here, and the problem to solve is to minimize the empty distances. We could also minimize the empty driving time, but in this case, I focused on distances. And so what we have is a typical routing problem, okay, which in optimization in mathematics have been widely studied throughout the years. So we have you have a lot of algorithms to solve them, and there are even a lot of software. There are commercial software and free software to solve this type of problems. The only thing is what we find here, which is that so when I thought about this problem, you actually have to make a difference between what I call the traditional versus on-demand. In this case, last mile transportation, but in general, traditional versus on-demand transportation problems. And let me stop here a little bit to make to explain what's the difference. So basically, traditional optimization or routing problems are, for example, the problem that Amazon faces every day. So you can make an order to Amazon, and normally they tell you, well, you get this delivered in 3 days. If you're a premium, next day. But it's always at least next day. So they have plenty of time, or well, they have at least some hours before they plan all the routes that they have in order to deliver all those orders. And they have all the information, so they know all the riders, they know all the drivers that they have. They know the fleet of vehicles that they have available. So traditional logistics problems, basically you have all the information you need in order to find the optimal solution. So as I said, the characteristics of these problems are you have all the information beforehand, and normally a solution is not needed immediately. So well, I've worked in my previous company in projects related to logistics, and there are some clients that think that half an hour in order to get a solution is good enough because the alternative to that is one person building those routes, and that takes longer. So so you don't need an immediate solution because it's for tomorrow. If we had to classify these sort of problems, again, it's routing problem here. Within optimization, these type of problems are a vehicle routing problem, which is a problem that is characterized by what we just said. So we have different depots or places where we have our fleet and different points that we have to visit, and we have to minimize distance in this case, okay? And in the case of traditional routing problems, the main challenge is actually being able to process, so take into account all the information we have, so all the orders that we have to deliver, so all the places we have to visit, and being able to actually find a solution that, if it's not optimal, at least is nearly optimal. Okay, so that's the main challenge there. But now this, so the only problem is that our problem, which is an on-demand, because you get an order and you have to service at immediately, it's not solvable by most of the software that is being developed for traditional ones. And why is that? Because, well, our problem on the on-demand transportation problem, it's an easier one from the point of view of the information you have available, because you only have vision of a time window, so it can be, I don't know, some seconds or some minutes, but you don't know, so you know what happened before, but you cannot change it, so you really don't care about what happened before, and you don't know what's going to happen in the future. You can forecast it, but you don't know it. Okay, so, and this is the problem that is called in literature is called the narrow vision problem, which is the fact that you, even though you have to solve a problem for a whole day, you only have a vision of a very, very short period of time, and if you make bad decisions, this could lead to very inefficient planning. Okay. So the characteristics, again, are the narrow vision. The orders have to be processed right, so in almost real time. well, when we classify this problem, it could be classified as a vehicle routing problem, but it really depends on the information we are going to take into account. Again, since we have only a vision of a very narrow window, we could go from a vehicle routing problem, but we could also see it as an assignment problem that we'll see today. Because actually, in a narrow window, you only have like some new orders that you receive, some drivers that are available, and you just have to match them, okay? And that's an assignment problem. So here, it may seem like an easier problem, but actually, it's a little harder to solve. It has two main challenges. One, which is how to overcome this narrow vision. So here, the main goal is, okay, how can I add more information to my problem to make better decisions? And more flexible solutions, decisions, sorry, so that if I make these decisions, so if I make one assignment, maybe I can reassign it later. That's one of the main challenges, and the other one is that you need an instant solution. So you get an order, and it cannot take you half hour to tell you, okay, so this is the taxi you're going to get, because otherwise you just don't wait, okay? So today we're going to be focusing on the on-demand transportation problems. This is just the map. This map is showing, well, I simulated the service orders that we get from 7 to 12 p.m. On a Thursday, based on some data that I used. And well, here what you can see is, what I wanted to show you is this narrow vision problem that we have. So here, once a service is no longer there, it's like you cannot do anything to change it. So that's one of the problems that we have here. Okay. Okay. So now I introduce you to the problem that I face every day on my bike. Then I translated it into a mathematical problem with the characteristics. Now I'm going to solve this problem, but I made some assumptions to make it easier for this presentation and for everyone to understand. And these assumptions are like my focus is going to be to minimize the total empty driving distance. Okay, you could take also time, but I decided distance for two reasons, because well, it's easier to see when you draw it in a map how solutions are different, and also because, well, if you drive less distance, well, it's less time that you are on a road occupying a space while you're empty. Then every trip is independent. Well, the two next points basically mean that a driver cannot be assigned to another trip order until he's idle. And then the type of fleet is the same for every driver, just again to make things simpler. And we will always have enough idle drivers to assign two trips. Okay, this is not in real time. This is not what happens in real life, because we can have peaks of demand where you don't have enough drivers for all your orders. But again, here for today, we're going to focus on this. Okay, and this is another, and this is the timestamp in which I'm going to focus again in order for make results easier to understand. Okay, so this is using CARTO Builder, and here what we have are the services that we have from 7 to 7:05 p.m. And you can see the initial positions of cars. They can be idle or not. And then we have in green we have the pickup points, and in pink we have the drop-off points. Okay, so basically, and well, in yellow are the minimum distance from pickup to drop-off points. And well, the idea here is, okay, let's see how we assign these cars to these services so that we minimize the empty driving distance. Okay, and I'm going to do this following different steps, okay, and I'm going to be adding more complexity to this. So the first thing that you could think, okay, I have this problem in which I need to provide a solution in real time. So the first thing you could think is, okay, if I think that I need to provide a solution in real time and customers' experience is important, so I want them to have a car as soon as possible. You could think, okay, so every time I get an order, I service it. So I find the driver which is closest to that pickup point, and I assign them. Okay, so you could think this is a good algorithm, and this is what we applied here. So Basically, there you can see the first 6 iterations of the algorithm, and basically this algorithm activates every time I get an order. So I get an order, I assign the closest driver who is idle. In this case, we got a solution with a total distance of empty driving of 181.67 kilometers, okay? And so this is going to be like our baseline model in order to compare how we improve with next steps. And so that's the first one, and we're going to see that even though it may seem that the greedy algorithm is good because you get an order, you service it, so it seems like you're going to really get your taxi faster. It's not necessarily the case, okay? Because well, because of this narrow vision that I told you before. Maybe if you wait 30 seconds, you'll have a taxi which is closer to you, and that can lead to lower distances. So the next step that I follow here is on the graph. There you can see the amount of orders that we have per every minute. So from 7 to 7:01, we have 25 services, then we have 14, and so forth. So the idea here is what happens if instead of servicing every time I get an order, I service it, I wait 1 minute, okay? So this means that at most you'll be waiting 1 minute to get what your taxi or your car is going to be, which is not much time. But actually this gives us more vision of our problem because, for example, in the first minute we go from servicing 1 by 1 to servicing 25 at a time. So you have a broader vision and you can make better decisions here. And that's basically what we are doing here. So we are going to increase the information we have, and we are going to postpone the assignments, and we are going to run this new algorithm every minute, okay? So basically here what I say is, so we have right now at every minute we have m trips, and so a number of trips and a number of drivers, and I have to make the best assignment here, which is to minimize the distance from their current position to the pickup point. And in this case, this is an assignment problem, okay? In optimization, it's a very widely studied problem. And there are specific algorithms for this, like the Hungarian algorithm. The only problem is the Hungarian algorithm is a very efficient algorithm, but if you want to evolve it, if you want to add more complex stuff to your model, it doesn't work, so you need to change it. So I'm going to use linear programming for this, which you'll see that it's a more general technique that allows you to add more complex stuff. Okay, so before we solve it and we see the solution, what's linear programming? So linear programming, which is also called linear optimization. So it's a mathematical method to achieve the best possible result, okay? In a mathematical model that is expressed with linear expressions, okay? In this case, in equations. And this is the form that a linear program has, okay? So I have my, well, this is how it looks like, and the components of a decision, of a linear program are the following. The first one is the decision variable. So normally in optimization, optimization is used to make decisions. So we have decision variables, which is what is it that I'm expecting my model to tell me what to do. And in this case is I have drivers, I have trips. So the decision I have to make is which driver goes with which trip. So my decision variable here are binary variables connecting every driver with every trip, okay? Then I have an objective function. An objective function is a metric that allows me to compare different solutions and decide which one is best. In this case, we're minimizing total distance. So my objective function, if I have two different assignments and I compare what are the distances that I cover with both of them, the one with the lowest one is best. So that's the idea of the objective function. And finally, the constraints, which the constraints basically tell you what solutions are actually doable or feasible that we call in mathematics. And basically this, there are many types of constraints, but we could think that there are two main types of constraints. We have physical constraints. In this case, it's hard to see, but for example, in a traditional logistics problem, a physical constraint is you cannot load more stuff in a truck than its actual capacity. That's a physical constraint. And you can have also business constraints, like for example, I don't want to service, I don't want to assign drivers to trips that take more than 20 kilometers. For example, that's a business constraint. That's a constraint that your company takes, and any solution that doesn't satisfy that constraint is not good enough for us. Okay. And well, linear programming. I forgot to say this before, but linear programming is not a new technique. Actually, it was well, it started in the 19th century, but it was mainly developed before the Second World War, and during the Second World War, it was used for positioning troops. And very interestingly, with the previous talk that we had here, it was the first problem that it was solved here was the diet problem, which is so in the UK, they had this problem, this economic problem, and they needed to feed their troops with good quality products, but to minimize the price of those. And basically, starting analyzing this problem is how they came with many of the techniques that were developed here. And also during the Second World War, it was when it was most developed. And why is it so powerful? Even though it's an old technique, because well, we could in optimization we can make a difference between exact and approximate algorithms, and this is an exact algorithm is the one that ensures that it has found an optimal solution, and this is an exact algorithm. The only problem is if your problem is too large, maybe it takes an infinite amount of time. So you have to be careful about this. Then also linear programming is a common mathematical language in optimization. So even though at the end you end up using another technique in papers, you'll find that many mathematicians use this language so that it's like the common language to communicate an optimization model. And then in the figure below, what I wanted to show is that in optimization there is a lot of different techniques, and linear programming and the related techniques are just a small amount, subset of those techniques. But the amount of problems, of optimization problems that can be solved with linear programming is, in comparison to all the problems, is very large. So it's actually very interesting technique. Okay. So so now we know what's linear programming, and let's model our problem and code it using. Well, I'm going to use OR Tools. OR Tools is an optimization solver developed by Google. Actually, it's not a solver. It's a wrapper of different solvers. Okay, so they have made this API to connect to different solvers, and both commercial and open source. So and free. Sorry. So it's a very interesting software. For Python, there is also Pulp, the Pulp solver, which is also very interesting. But this one is more efficient because of how it connects with the source solvers. Okay. So well, we are going to be using the PyWrap LP, which is the solver for linear programming, and this is how you initiate it. In particular, we're going to connect to the source solver, the CBC solver, which is a free solver. It's amongst the free solvers is one of the most powerful. It depends on the problem, but it's one of the most powerful. So again, let's try to identify all the different parts of our problem. So we have the different indices or sets of our problem. So we have the orders and, well, you should say drivers. And then as input data, we have the distance from the current positions of my drivers to the pickup points of the different orders. Okay. So and then what I need in my problem, I need my variables. I have a set of binary variables that, again, as I told you before, they're connecting my drivers to my services here. So they are binary variables that are going to tell me whether they are or not matched. And that's how you define them with this PyWrap LP library. And then my objective function, which is I want to minimize the total distance, the total empty distance, which is that function. Okay, and that's how you code it with PyWrap LP. It looks ugly actually when you code it, and this is, well, because this is a general library. Actually, if you, especially with commercial solvers, they have a very beautiful way of writing this, and it's much easier. But again, it's better. So it's interesting to use this wrapper because then you can connect to different solvers and compare the performance. Then in terms of constraints, So we have the first constraint that we have here is that every driver is assigned to at most one trip. This may seem obvious, but you have to tell the model how your system may work, because otherwise the model doesn't know how it has to work. And that's how you write it. So you say, so for every driver, the sum of the services that I assign him, it's smaller or equal to 1. And then again, every trip is assigned to at most one driver. So for every trip, the sum of drivers assigned to that trip is smaller or equal to 1. Okay, and that's how you translate it with this library. And finally, we want to assign as many trips as possible. One of the assumptions I made at the beginning is that we're always going to have idle drivers, but in case we didn't, the maximum number of trips that I can assign is the minimum between the number of idle drivers and the number of services that I have. So there, what I'm saying is I need to make all these assignments, okay? And that's how you do it. Okay, so so now we know what's linear optimization. We have coded we have written our model in mathematical notation. We have coded it, and now we want to solve it, okay? And well, to solve it with this library is very easy. You just call solver solve, and you have a solution. You check if it's optimal or not, and that's it. But now let's see what happens behind the scenes, so what's really happening and how you solve this problem, okay? So in this case, since we're working with linear optimization, what we have, it's like every constraint is in a hyperplane of the space where you're working. So basically, we have a lot of hyperplanes that are intersecting one with another, okay? And you end up with a figure like the one you have on your right. Which it should be in 3 dimensions, but it could be in any dimension there, and what you end up with a polytope, okay? The interesting thing about this is that there is theorems or a mathematical result that states that the optimal solution is at one of the extreme points of that polytope, which is basically at one of the intersection of these many hyperplanes, okay? And that's good because that reduces your search when looking for the optimal solution. Okay, and there is also one interesting characteristic, that is that at these extreme points, I know that if I have m constraints and n variables, I know that I am going to have m variables with value different, greater or equal to 0, and I'm going to have n minus m, so the number of variables minus the number of constraints, variables that are going to be exactly 0. And this property is used to solve this algorithm. And the way you solve it is basically, so you start from one extreme point and you start exploring different extreme points until you find one in which you see that there's no potential of improvement, okay? And when you reach that point, it's when you're done, okay? Now, this is how you solve the problem for when all your variables are continuous. The problem is our variables are not continuous, are binaries, or they're integer. I'm not going to dive deep into this, but basically, if you have integer variables, that means, you need another technique, which is based on the simplex algorithm, but basically you need to build this type of trees with branch and bound or other more evolved techniques that will rely on this branch and bound algorithm, but basically it gets more complex, as you can see, because if all your variables are continuous, you start and stop in the subproblem 1. If you have integer variables, this is what you get. Okay, and this is just a quick note about what makes a good solver. There's a huge difference between commercial and free solvers when it comes to linear programming. And these are the 3 things that I advise you to take a look at if you want to see if yours is good or not. Okay, which is the pre-solve, which is how your solver tries to reduce this polytope in order to make it faster to reduce. And I can tell you, with a commercial solver, you can have the problem solved in a matter of seconds, and with a free one, it can take minutes. Okay. Then the heuristics that it used in order to find these integer solutions, and then the parallel communication between the different trees that we saw in the previous one. Okay. Again, very fast here. There's a good thing about this assignment problem, which is that our matrix here is totally unimodular, which basically means that every sub-matrix, every square sub-matrix has determinant 1, 0, or -1, and this basically gives us a very cool property. And for our problem, we can define all our variables are continuous, and yet our solution will be integer. So this is a very interesting result because it makes it easier to solve and actually a very efficient algorithm for the problem we're solving. Here, so now we know how this works. We solve it, and this is the different results we get with the greedy algorithm and with the assignment one. Okay, we see a 13% of improvement, and for example, in the northeast part of the map, you can see that with the greedy algorithm, we had a very inefficient assignment that now we have been able to improve it. So that's a good thing. It's very important to visualize it because it allows you to really see what's happening if your algorithm is working or not. And yet, a step 3. Which is, so step 3 is still work in progress, okay? But I'm going to introduce you to the idea that we have here, which is how we can still improve this algorithm. So right now we have been focusing on assigning the driver that is closer to it, but actually we need more information about what's happening in order to improve this algorithm. And this is the supply-demand matching. So I want to forecast what's the demand going to be like in the next 30 minutes or 60 minutes so that I can make better decisions on how to move or how to assign these drivers, okay? So for that, you need to build a reference grid so that you can calculate you can forecast the demand in every of those grids, and then use historical data of the historical orders that you got, plus enrich your data. And this is one very interesting point that we always do at CARTO, and this is something that I not always did in my previous companies, but it's very interesting, which is enriching your data, which is in this problem is very, very important. And why is it important? Because if you only take into account your historical data of the orders you got, you will probably be biased because you depend on where your drivers have been. You don't know where your competitors have their cars, so you can be biased by where your actual demand is, but you don't know if there's more demand yet that you can have. Okay, and in this case, one of very interesting source of data that we could use to enrich our data is footfall data and the OD metrics data that I will show you here. So here, what we can see is the amount of people. So well, actually, this picture is better. So here, what we can see, for example, is in a 250 by 250 meters, so 250, sorry, by 250 meters grid, and we have the estimated, sorry, not the estimated, the actual data on the aggregated number, sorry, of visitors that we had at every of these cells on a Monday morning, on a Thursday evening, on a Sunday night. So here you can see that there are different patterns of where people are. And actually, we can also have this OD metrics information that, well, it's very small, but there's a cell painted in light blue. And here what we can see is so people that are that visit that cell, where they come from. So this is very powerful because, for example, on a Thursday evening, if you know where people at a specific place, for example, you look for a working place and you see, okay, where people come from, you can see where those people come from, and you can take that to enrich your data and actually make better decisions on where you should place your cars or your drivers to get more services, let's say. So the idea here is that we would end up with a forecasting result, okay? Again, this is work in progress, so this is a simulation that we ran in order to test if this idea was good. So we would end up with this forecasting result where we can see the amount of orders that we could expect in the following 60 minutes. And then we have where our cars are positioned. So in red, I would have those that I want to get to the city center because I'm going to have a lot of demand there. And in purple, I have the cars that I want to keep, if I can, I want to keep them there because that's where my demand is going to be in the next hour. So if I take them far from the city center, I'm going to increase the number of empty kilometers that they drive, okay? So, and just to show you, for example, with the Hungarian algorithm that I told you before was like the first approach that you can follow to solve this assignment problem. This cannot be done. So the good thing about linear programming is that it allows you to make this type of constraints. So here we have a logical constraints that you can linearize, and well, this is how you transform it. So again, next steps, we could, we made a lot of assumptions here. So you can, not all these assumptions may make sense for your business or your problem. So again, this problem can get a lot harder. And the good thing about linear programming is that you could add all these components to your problem. As some takeaways, well, the power of linear programming. Then visualization is very important when solving this type of problems to get an idea of what's happening around in your city, where people move, where you get the orders, and so forth. And then data enrichment to avoid this bias that you can have if you only use your own data. So, well, thank you very much for listening.
Thank you very much for this great talk. Thank you.
I have a few questions. What is your customer?
No, there's no customer here.
Okay, then the second question is that, did you consider time? Because that I have watched a movie called The Butterfly Effect. If you change something, something else will change. So for example, if you suggest people to a different route, could be the new route will become very crowded. Then what? Do you have a real-time adjustment? For example, if I go to my office in the morning, right? You know, first of all, it tells me, you know, if I start to leave at 8:15, and it tells me 25 minutes in the beginning, but gradually it will increase 15 minutes. But if I start to leave at 9 o'clock, it will tell me 45 minutes, but gradually it will become 25 minutes.
Yeah.
So this time is also one important dimension. Do you also adjust this at real time? So did you have actually a test of the whole process? I mean, what you said is just one prediction. Did you also have a final day-to-day final adjustment to look at it overall? And also, like when there is only one people use your software, and also everybody use your software, and also if there is an AI system, everybody take this. This will all be different things, you know, this time.
Okay. Well, if I don't remember all your questions, I'll ask you later. So the first thing about time, as I said before, yes. So we could have thought about time. The only thing is we chose here distance, not because this is the final product, but because it's easier to visualize. So it's easier to visualize in a map that you're actually taking a shorter route, so that actually you're taking a shorter distance. But of course, in this problem, it makes more sense to take the ETA as so the expected time of arrival from where your driver is to the pickup point. That's what actually makes sense for this, and that is what should be taken into account. And of course, in real time, so that you can calculate that in real time, and you know what's the expected time of arrival of all the drivers, and you actually make the best decision based on real-time information. But again, here, it was just to show you this, and I thought it was easier, because when I draw the results, when I plotted the results with distance and with time it's not always obvious that you are actually making the shortest path. So that's why I chose here distance, but yes, it makes sense. And can you repeat the next question, sorry?
Yeah, so basically the other thing is that, did you have a final evaluation? So for example, for a whole day, if people actually use your software, will that actually improve things? So because if everybody's changing real time, it could eventually waste more time. You never know.
So if everyone,
if everybody is using this, so supposing, right, if you are going to stock market, you say, okay, this stock make money, and it change every second. So this now there's also, you know, the stock. If you change different stock, it will cost some commission fee. So, you know, if you change too fast, then it will not help you to save time. So what is time spent time? And also, did you have an evaluation eventually if there's a whole region use your software, will that really save time or not?
Yeah, well, at this moment it's not being used. So the idea here is how you test this type of problems. So the different from traditional ones here, you need to simulate what's happening in a city. So we could use, for example, discrete event simulation to simulate what's happened throughout the day, and you can actually measure this sort of thing. So what happens if, Yeah, so we would use discrete event simulation through a whole day and simulate what happens, and we've tested like that. But I don't see the problem with what you say about if everyone is using this. So I don't see. I mean, if you have a city and people are using this type of service, suppose that we increase the demand, for example. But I mean, this is actually what happens today with these rideshare companies. The only thing is they're not located. I mean, they try to locate them intelligently, but we're here trying to go a step further in how to locate those drivers. But the problem is the same as we have today. So you can have, if there's a peak of demand in a certain place of the city, you may end up with not having enough drivers there. So that can happen.
So thank you very much for the talk. My question is about the preparation of data for the linear programming algorithm you're using. So you mentioned that you have this assumption that you always have idle drivers.
Yes.
What if you could actually consider to be idle drivers, and then you could add the delay for the possible drivers to the end result?
Sorry. So how did
No,
we
I
do
mean
it?
as a suggestion. Maybe you could also add to be idle drivers to the list of drivers as a possible candidate.
Yeah. Actually, what we did. So actually, here when we simulated this data, it's not that if we have in total 100 orders in these 5 minutes, we have 100 drivers. It's not like that. We actually have less. I don't know the number, but we have less. And what we consider is, okay, if this driver is assigned to this specific travel, I know when they are going to finish. So I know when he's going to be idle again, so that I can assign them to a different one. That was your suggestion, right? Yeah. Thank you.